Welcome to the deep dive. Today we're looking into something really fascinating, gravitational microlensing.
Right. It's this idea that the universe can kind of act like its own telescope.
Exactly. Using gravity as the lens. We've got SA hashtag 84 here, Gaia's microlensing events, and we're going to explore what the Gaia mission is finding out.
Yeah, so the core concept is Einstein's idea, really matter warps space-time.
And that warp bends light passing by.
Precisely. So imagine you have a star or, some massive object in the foreground,
Okay.
and it lines up almost perfectly with a star much farther away in the background.
A chance alignment.
A very precise chance alignment. The foreground object's gravity bends the light from that background star.
So what does that look like from here?
Well, it can make the background star look distorted, maybe even split into multiple images. And crucially, it often makes it look brighter, significantly brighter sometimes.
So it's like a cosmic magnifying glass, but instead of making the image bigger, it just cranks up the brightness.
That's a great way to put it, yeah. The main thing we notice is this change in brightness, the photometric effect.
Photometric, right?
We see the background star get brighter, then fade back down. And this whole event, it can take hours or days, sometimes even years.
Years. Wow.
Depending on how things were moving up there. And at the peak, yeah, the star can appear many, many times brighter than normal. It's quite dramatic.
Okay, so astronomers on the ground have been watching these brightness changes for a while now. But the essay points out something Gaia is special at observing: astrometry.
That's right. Microlensing doesn't just change the brightness, it also causes a tiny, tiny shift in the apparent position of the background star.
Like its center of light wobbles a bit.
Exactly. That's the astrometric effect. Now, this shift is incredibly small.
Too small to see from Earth.
Pretty much impossible to measure accurately from the ground, yeah. Our atmosphere just blurs things too much.
But Gaia, being up in space,
Gaia is different. It's making these ultra-precise position measurements, so it was actually designed, in part, to be able to detect this very subtle movement. SA hashtag 11 goes into that a bit more.
got it. And something else you mentioned earlier, it's not always just a single star acting as the lens, is it?
No, definitely not. Sometimes the lens can be way more complex, maybe a whole cluster of galaxies.
Right.
Or, more relevant for finding planets, maybe it's a star that has planets orbiting it.
Okay. And that changes how the background star brightens.
It does. The pattern of brightening, the light curve, becomes much more complicated, less like a simple smooth bump. It might have extra little peaks or dips.
And that complexity is the key.
It's been a hugely successful key, yeah. Those unique patterns are signatures that tell us there's more than just a single star doing the lensing.
So that's how they find exoplanets with this method.
Exactly. Ground-based surveys, think OGLE, MOA, KMT. They've been monitoring millions of stars looking for these specific, complex, brightening signals.
And finding planets that way. How many have they found?
The source says over 350 exoplanets discovered just through ground-based microlensing surveys. Pretty impressive.
That really is. Okay, so that sets the scene. Let's dive into Gaia's specific role, drawing from SA hashtag 84. It sounds like finding these events was a big scientific goal for Gaia.
Oh, absolutely. It was built into the mission plan. They knew Gaia would see these brightening events, and they wanted a system ready to catch them quickly.
So not just collecting data, but analyzing it fast.
Right. It required really careful calibration of the instruments, sophisticated software to spot these changes against the background noise, and crucially, a system for sending out rapid science alerts.
Like a notification, hey, look over here.
Basically, yeah. If Gaia spots something suddenly getting brighter, like a potential supernova or a microlensing event, an alert goes out pretty quickly.
So other telescopes can jump on it.
Exactly. Allows for follow-up observations from the ground. Our source mentions Hodgkin et al. 2021 and SA hashtag 36 for more on that alert system.
And has it been working? Are they finding events?
Oh, yeah. By September 2021, the pipeline had already flagged nearly 50 microlensing candidates.
50 already, wow. And where were they finding them mostly?
Mostly where you'd expect in the plane of the Milky Way, and especially concentrated towards the galactic bulge.
The center of the galaxy, where it's really crowded with stars.
Right. More stars mean more chances for those near-perfect alignments needed for microlensing. Simple statistics, really.
And the numbers kept climbing after that.
They did. By mid-2022, the number of candidates reported via Gaia alerts was over 400.
400. Any particularly interesting ones mentioned?
Yeah, the essay highlights a few. Gaia 6i was cool. The lens wasn't just one star, but a pair of stars orbiting each other, a rotating
The
binary.
binary lens, that must make the light curve really
It
complex.
does. Then there was Gaia 18 CBF, which was notable for being incredibly long. The brightening lasted 491 days.
Wow, over a year.
Yeah, nearly a year and a half. And another one, Gaia 19, and was just remarkably bright when it peaked. Reached about ninth magnitude.
What can we learn from those specific cases? Like the binary lens one.
Well, Gaia Saxidia, the binary lens, lets us probe the combined gravity of two stars and study how they interact, maybe learn about binary systems in general.
And the really long one, Gaia 18 CBF.
That super long duration likely tells us something about the relative speed between the lens and the source star. Maybe they were moving very slowly relative to each other. It could hint at the masses or distances involved.
Okay. And the bright one, Gaia 9 peeled.
A very bright event means you get really high-quality data, very precise measurements of the brightness changes. That precision can reveal subtle effects, maybe even hints of planets around the lensing star if they're there.
Right. Now, you mentioned ground-based surveys like OGLE are also finding these. How does Gaia compare? Is it finding more, less?
That's a key point. Gaia isn't necessarily observing more frequently than dedicated ground surveys.
Okay.
Yeah, those ground surveys might look at the same patch of sky every single night. Gaia is scanning the whole sky, so its visits to any one star are sparser, irregular too.
How sparse are we talking?
Well, over the first 34 months of data, that's what's in Data Release 3, or DR3, the average star was observed maybe 40 times.
40 times in almost 3 years.
Yeah, and actually, in the really crowded bulge, it was often less, maybe around 20 times on average. But in other parts of the sky, it could be more like 100 times.
So ground surveys look more often. What's Gaia's edge then?
Gaia has some unique strengths. First, its brightness measurements, the photometry, are incredibly precise, way better than most ground surveys can achieve routinely.
Okay, precision. What else?
It can see a huge range of brightnesses, faint stars, bright stars. It covers the entire sky, not just targeted fields. And importantly, it measures brightness in 3 different color bands, simultaneously G, GBP, and GRP.
3 colors at once. Why is that useful?
That color information tells us about the temperature and type of the background star, which helps constrain the models of the lensing event. It adds another layer of information.
Gotcha. And you mentioned Data Release 3. Is there more coming?
Oh, yes. The next big one, Data Release 4, is going to be huge for microlensing.
How so?
Because DR4 is expected to include detailed astrometry for many stars over time, those tiny position shifts we talked about earlier.
The astrometric microlensing Gaia was designed for.
Exactly. And potentially spectroscopy, too, information about the light spectrum. Combining the brightness changes, the color changes, and the position changes will give us a much, much more complete picture of these events. It could really help nail down the mass and distance of the lensing objects.
Okay, that sounds powerful. Let's dig into that Data Release 3 survey itself then. The source mentions it involved analyzing data for 2 billion objects.
2 billion, yeah. Over that 34-month window from 2014 to 2017, the specific processing unit, called CU7, generated light curves, records of brightness, changes for about 1.8 billion of those. An absolutely massive data set.
Mind-boggling numbers. How did they even start to look for microlensing and all that?
A team led by Warzikowski, their 2022 paper is cited, tackled this. They used 2 main strategies, creating 2 samples. Sample A was purely based on Gaia's data.
An automated search.
Right. And Sample B was built using events already known from other surveys, mostly OGLE plus a few others.
Okay, let's break down Sample A, the automated search. It started with something called the extractor.
Yep. The extractor's job was to sift through those 1.8 billion light curves and pull out anything that looked like it might be a microlensing event. Basically, a one-off brightening.
How did it decide? What was it looking for?
It looked for a few key things using the data from all 3 color filters, G, GBP, and GRP. Did the star have some points significantly brighter than its baseline?
Okay,
Did this brightening happen in all 3 colors at roughly the same time?
makes sense.
And was the star pretty much constant in brightness outside of that single brightening event?
Right, rule out stars that are just normally variable.
Exactly. This first pass, this extractor step, cut down the 1.8 billion sources to a more manageable 98 million candidates for a closer look.
Still 98 million. That's a
Yeah.
lot of candidates. What happened next for Sample A?
The next step was the heavy lifting, detailed modeling. For those 98 million, they tried to fit mathematical models of microlensing to the actual brightness data points from Gaia.
to see if the shape of the brightening matched the theory.
Precisely. Does the light curve look like what we expect from standard microlensing, or maybe a more complex version? That helps confirm if it's real lensing or something else.
Okay, that's sample A. And
Yeah.
sample B was different, based on known events.
Correct. Sample B was essentially a cross-match. They took known microlensing events, mostly from the OGLE-YV survey, 1527 of them, plus a couple from AUS-SSN, and 7 that Gaia's own alert system had already flagged during that DR3 period.
Right.
And then they looked for those specific events in the Gaia DR3 data to see what Gaia saw.
So combining Gaia's view with what others had found makes sense. What were the overall results from combining sample A and sample B?
The final tally was pretty significant. They found 163 events just from the automated search in sample A.
Yeah.
And they characterized 233 events that came from sample B, the known ones.
Was there overlap?
There was. 33 events were actually found independently in both samples, which is good confirmation.
So the total number.
Adding them up and removing the duplicates gives 363 unique microlensing events identified in Gaia DR3. They're now cataloged as Gaia DR3 U-lens, followed by a number.
363 events from this one data release. How many were totally new discoveries?
That's one of the really exciting results. 90 of them were completely new, never reported before by any survey.
90 new ones. So Gaia is definitely finding things others missed.
Absolutely. The other 273 had been independently seen by surveys like OGLE, ACES, ZTF, which is also important. It validates both Gaia's findings and the ground-based discoveries. It shows Gaia's power, maybe due to its all-sky view or its unique sensitivity.
Where did these 363 events tend to be located? Did it match expectations?
It did, mostly. About two-thirds of them, 228 events, 63% were found towards the galactic bulge.
Towards the center again.
Yeah, concentrated mostly within about 7 degrees of the galactic plane, latitude-wise. That distribution roughly follows where the stars are densest, just like we discussed.
And the rest?
The others were mostly still relatively close to the galactic center in terms of longitude, generally within 50 degrees, and also mostly near the plane.
Does Gaia give us distances to these things?
For the background source star, yes, often. Gaia's earlier data release, EDR3, had parallax measurements, which give distances. They were able to get source distances for 346 out of the 363 events.
That's really useful for modeling the event, I bet.
Hugely useful. Knowing the source distance helps constrain the distance and potentially the mass of the lens itself. And seeing this concentration in the bulge helps us map out how mass, including dark objects, is distributed there.
How complete do they think this survey is? And are they sure these are real microlensing events? Any false alarms?
They estimate the completeness varies. It's maybe around 30% in the superdense bulge, but potentially up to 80% in the less crowded disk regions. And it's more complete for events that last longer, say more than about 60 days. They seem pretty confident about the identification. They estimate fewer than 1% are likely false positives.
Less than 1% false positives is pretty good.
Very good, yeah. It means the sample is quite pure.
The essay also pulls out a few specific events as examples. Can you remind us of those?
Sure. There was hashtag 001, Gaia DR3, ULNS 001. That one was notable because it was a brand new discovery in DR3, missed by other surveys, really shows Gaia's reach.
Okay.
Then hashtag 0002 was interesting because another survey, ATLA's, had initially thought it was just a regular long-period variable star. Gaia's data helped correctly identify it as microlensing.
Ah, correcting misclassifications.
Exactly. Event hashtag 007 was one confirmed independently by OGLE. Good cross-check. Number hashtag 259, also known as Gaia 17 Aqua, was one of the 7 events that came from Gaia's own science alert system during the DR3 period. Shows the alert system works.
Right, caught in near real time.
And hashtag 023 was a long-duration one, first started by ASOS-N back in 2016, and also seen by OGLE, so that one had multiple witnesses, so to speak.
It's cool how these different projects complement each other. The source also mentioned animations.
Yeah, apparently the University of Warsaw microlensing group, who are heavily involved in OGLE, have put animations online using real Gaia data for some events.
Oh, that'd be neat to see. Visualizing the lens.
Exactly, showing how the light bends and the brightness changes as the lens passes in front of the source probably helps get an intuitive feel for it. Worth looking up if you're interested.
Definitely. And we have a figure here showing some of the actual light curves from the paper. The brightness plotted over time. You can really see that characteristic brightening and fading.
Yeah, you can see hashtag 023, the long one, and hashtag 259 from the alerts number, hashtag 007, hashtag 002, hashtag 001. They all show that distinctive bump.
It's still kind of amazing that just watching a star get brighter and dimmer like that tells us about invisible objects passing light years away.
It really is. And often, as you see in that figure, data points from different surveys are combined on the same plot. That collaboration really strengthens the analysis of each event.
Okay, so let's wrap up this deep dive. What's the big picture here? What's Gaia's main contribution to microlensing been so far?
I think it's fair to say Gaia's contribution is already transformative, even before we get the full astrometric results from DR4.
How so?
Well, this DR3 survey alone significantly boosted the number of known events, finding almost 100 completely new ones.
Right, the 90 new discoveries.
And Gaia brings unique capabilities, that amazing precision, the all-sky view, the multicolored data. It complements the ground-based surveys perfectly, finding events they might miss and providing extra detail on the events they both see.
So it's giving us a more complete census of these events across the sky.
Exactly. And remember what these events represent.
They're like probes, right? Showing us where the mass is.
Precisely. They let us study the distribution of all kinds of matter stars, sure, but also things that don't shine brightly on their own, or maybe don't shine at all.
Like brown dwarfs or even black holes, maybe planets just floating freely.
Potentially all of those, yes. By counting the events, looking at how long they last, where they happen, we learn about the populations of these objects throughout the galaxy. It's a way to map the galaxy's structure and its hidden contents.
So as you listen, just think about that. These random alignments, these subtle flickers of light from distant stars, are literally revealing the invisible scaffolding and unseen inhabitants of our Milky Way. It kind of makes you wonder, what other cosmic secrets are out there, hiding in plain sight, just waiting for us to find a clever new way to look? Thanks for joining us on this deep dive.